It's really important that you know this because whenever we use Desmos, we're going to have to type in basically that equation. On the calculator, you don't, it's kind of like stored, but I still think Desmos is easier to use. So, sine functions are so cool because they can be used in so many different things that have nothing to do with triangles anymore. So, it is great for modeling lots of different things. For example, the amount of daylight that we have. So right now, our days are getting longer. We're getting like up towards the top on June 20th or 21st or whenever our summer solstice is, then we'll be at the maximum point of our sine curve, most hours of daylight. Then it'll start to go back down. And if you really think about it, if you think about it always, which daylight savings time actually doesn't change your number of hours of daylight at all, but your perception of it does change because a lot of us are asleep for those morning hours. So, if you kind of think about the daylight, to me, it always seems like all summer long, it seems like it's about the same. It's not. It's a little bit longer on June 21st, but it's, around that time, it seems like you got a lot of daylight, right? And then it seems like when it does start, days do start shortening, it seems like it goes so fast. And if you think about what a sine curve looks like, it's not really steep up there at the top. Like it is changing, but it's kind of flat, But then when you get to the part of the sine curve where it's steeper, that's when those hours of daylight are changing really quickly. So, and then you throw daylight savings time in on top of that, and that makes it seem even more like it really dropped off because you're hitting, losing an hour at that point, although the actual amount of daylight is only changing slightly. So ocean tides can be modeled by this, roughly. Ocean tides, we used to do a project, and we just don't have time to do it anymore, where we actually went and looked at NOAA data and predicted ocean tides, but they vary. They're not perfectly sinusoidal, and particularly one year I had students do this project, and NOAA has these websites where you can look at the height of the tide in basically almost anywhere in the United States. So one year we did the project, and the kids picked a place in Florida, and a hurricane had just came through, and their data was, which I let them do it even knowing that happened just because I wanted to see what it would do, but their data was all over the place. It didn't look like a sine curve. It was way high for a while. So definitely weather can affect it, and it's not going to be perfect, but it more or less follows a sine curve. Temperatures, either throughout the day or throughout the year, are going to follow this. So, of course, weather, again, would play a big role. Temperatures would, be lower at night, higher during the day, lower again at night, higher in the day. That's going to vary a lot based on weather. So that would be less closely tied. But if we look at yearly temperatures, we know that's going to be colder in December, hotter in July, colder in December, and just continue that pattern. Not perfectly every year, but overall follows that pattern. It's one of the things that must be considered, like this past winter was a very warm winter because we didn't have any snow at all, and we had a lot of warmer days. So, it would be a lot less warm, and it's really important not to make assumptions off of one winter. Tom used to be a custodian here. I think he's passed away now. He was an older man. This is whenever I first started working here. And I was upstairs over there. This part was being built. So I was upstairs over there. Miss McComb was across the hall from me. And Tom, he'd come in and clean my room after school. And he'd say, sure is hot today. Maybe there's something to that global warming. And then he'd come in on a cold day and he said, sure, it's freezing today. I don't think there is anything to that global warming. And it would drive Miss McComb crazy. It amused me. But it would drive me. She would want to explain to him why he couldn't make those assumptions off of one particular day. But it was, interesting. He was an older gentleman that, was probably not going to change all of his opinions based on that. But so I just found it amusing. So anything periodic can be modeled with this. One application we won't get into a lot, but is very applicable, are like wavelengths for science. The main reason we stay away from that type of wavelengths for science stuff is because you got to get into a lot of science to really apply it, and a lot of times I do not have the background to deal with that. Plus, nor do I have the time. Like, even if I did learn it, I don't have the time to teach you all you need to know to be able to use that. But certainly there's a lot of application for things like that in a lot of sciences when you're talking about wavelengths of different light, radiation, different types of things like that. So it's pretty interesting. To me, it's so cool how sine functions can show up in all kinds of places that don't seem like they have anything to do with a triangle anymore. So let's look at how to do this. So we're going to do this first on the calculator. All right, so have you guys used L1 and L2 in the calculator before? We as a math department have been getting away from using the calculator. There are two reasons that I want to show you how to do this on the calculator. The first of those is I am not sure what colleges are doing. I do know that if you go take stats at Surrey, they make you buy a TI-84 calculator. I know when I was in college, you definitely had to use the calculator. And I know if I was a college professor, unless I had something where Desmos was built in, I would be hesitant to let you use Desmos on a test, because that would also give you access to the whole internet. So there is a chance, particularly if you get some old school professors as well, that they're going to expect you to know how to use the TI-84 calculator, so it won't hurt you to go through how to do this. I don't care. You can use either way. I just want to show you both here. So on the calculator, if you want to do any type of regression, a regression is when we take data points and we fit a curve to it. We're going to be looking at sine regression. So we're going to take data points and the calculator is going to fit us a sine curve. But we could take data points and fit a line, or data points and fit a quadratic. You've done that in your other classes, probably on Desmos and not the calculator, but you've seen that before. So to do this on the calculator, to get to L1 and L2, you're going to press Stat, which is the button right here, 2 over from the green button. And then you want to hit Enter for Edit. So let me write that down there, because it's Stat and then Edit. And this should get you to a list 1 and a list 2. It is probably blank because we don't use these calculators for this anymore, but it might have some numbers in there. If it does have numbers, you can just hit delete, like if it has numbers there. If you just go to the number and hit delete, it'll clear those out. And so we're going to put our data in here. And one wrong number will ruin your data on here and make everything wrong. So I suggest looking back through and make sure that you've got all of your numbers right. What have you done?
I don't know. Put in letters.
Oh no, you deleted out all of yours.
Okay. But
Or somebody has. If that happens, you'll just that go down here to number 5, which is set up editor. Then if we go back, there. Somebody had deleted all your lists out, and it's wanting you to name them again. So. Now, on your homework, there will be questions that have like a part A, B, C, D, E. So if you mess up your regression, it's going to mess up all of your answers for that. I am not going to do that to you on the quiz. Each question will be independent of each other. So, like, you'll have one where you got to do a regression, you'll have to type in the numbers, but then, like, the next one won't ask you to use that regression because it makes it a great nightmare for me because I either got to, like, count it all wrong if you miss that part, or I've got to go back and, like, use your line to, and that's terrible. So I just avoided that by putting all the questions have different ones. All right, so everybody got their data in? All right, we are going now to hit Stat. And then up here at the top you see Calc. You're going to go over to Calc. And this is where all of your regressions are listed. So if you want to do a linear regression, you'd pick 4. Quadratic regression, you'd pick 5. Cubic would be 6. And so this is where these are all listed. We are going to go down here to the very bottom, C, sine reg. That's your sinusoidal regression. The calculator only does sine. It will not do a cosine. But that's fine because you can always get a sine to work, right? It doesn't matter. So we're going to hit Enter. And then just hit Enter again. If you have a fancy new calculator, you may get a screen in between that where it has like a Y1 and a L. Just go to the bottom and tell it to calculate. Alright, and you can see I rounded these off to 3 decimal places just because it gave me such long numbers. It'll give you the A, B, C, and D values for this. Everybody get it to work? Okay. Yes. Yes. Yes, this is why some of it is going to be calculator inactive for you tomorrow on the quiz. But yes, like if you were given this, like if you had a graph and you were trying to write the equations like we were doing yesterday, you could just take some of the points from that graph, put them into the calculator, and get it to do a regression for you. Now you would have to pick, like, if you pick only like x-intercepts or something, it wouldn't work. You'd have to have like some maximums, some minimums, and stuff in between, but it would do that. But part of it's calculator inactive, so you can't do that on that. All right, so this is how you do it with a calculator. Let's now flip over and do the same thing with Desmos. A word of warning, Desmos is going to give us a very slightly different answer. Desmos, I think, uses a different formula or like a different method for getting the regression. So sometimes the numbers are slightly different. Like instead of a 1.598, it might be a 1.597. But they're usually still pretty close here. So let's see how close it gets here. So Desmos, you're just going to hit the plus. You're going to put it in a table, and you're going to put your data in. The calculator will graph for you, but gosh, Desmos is so much better. You can see the points popping up as you go. If you mess something up, like if you accidentally put a 1.88 instead of 10.88, you can see pretty easily that it's wrong. I prefer Desmos, but okay. So on Desmos, once you have your data in, you are going to go to the second line. You're going to type in Y1 squiggle. To get that subscript, just type a Y and a 1. If you type a number after a letter, it'll make it a subscript. And then do A sign BX plus, or do BX1 plus C plus D. It's just your formula for the sinusoidal function, but instead of equals, you use the squiggle, which is shift and that corner key there below escape. And then instead of using an X and a Y, you got to use an X1 and a Y1 because that's the way Desmos labels its table. And you can see it fits so nicely. We'd call it like a curve of best fit because technically a line would only be a line, but yes. It's very similar to a line of best fit. Like if we wanted to do a line of best fit for this, we do Y1 squiggle MX plus B. We wouldn't do that for this data because it'd probably give you the like equation of the midline because it's halfway between, which would be useless for this other unless you need to know the midline. But yes, this is the same way that you would do for like lines of best fit. You can do it for exponentials, you can do it for quadratics, you can do it for lots of different things. I think it still works if you do a cosine, but just let's always do sine because that's the way I've set the answers. So there's not really an advantage to using sine over cosine because even though this might look like, well, maybe it's a low point right here, it might not exactly be. So just use sine for everything. All right, and you can see here for our numbers, A is the same, B is the same. Oh, wait, hold on. Yeah, they're all the same. That's what I got on the calculator, I believe. You can see, but like it doesn't rounding to 3 decimal places, it doesn't actually change it. But like if you look at C, I've got negative 1.60298, and here I've got negative 1.6030016. So there's a little bit of variation. Sometimes it will affect what you've got if you round to 3 decimal places. Sometimes it will not. I will go back and adjust for that on the quiz. So no, I can't remember which one I used to do the answer key, but it won't let me put 2 answers in there. So so it may look like you have missed a regression problem, but it's just because you used Desmos or the calculator instead of the other. So I'll go back and adjust for that. All right, so let's talk about using this to answer some questions. Okay, so as far as amplitude, period, phase shift, vertical shift, midline, all of that, it's just the same rules as what we were doing before. Your numbers are just uglier. So if I want to know the amplitude for this, it's going to be 1.598. Right? If I want to know the period, I do 2 pi divided by that number in front of my x, which is 0.512. And we're going to do everything in decimals here. So 2 pi divided by 0.512. It's going to give us 12.272. If we round to 3 places. phase shift is going to be negative 1.603, our C value, divided by 0.512. So negative 1.603 divided by 0.512. It's going to give us negative 3.131. Or I'm going to say left. No, it'd be right. It's opposite, isn't it? I'm just going to ignore the negative. And then I'm going to say it's right. 3.131. And our vertical shift would be up 12.116. Midline would be y equals 12.116. So as far as it asking for any of those things, you just do the same thing that we were doing yesterday. Now, here's where it's going to be different for this. Now I'm going to ask you some questions that don't necessarily say they're asking you for amplitude, period, phase shift, or vertical shift. Or maybe they do, but they're asking it in context. Okay? So, let's think about what we have here. Okay? I went ahead and just put the answers that we got. The midline is at y equals 12.116. What does this mean in context of the problem? I'm going to go over here to Desmos, and I'm going to type it in. Y equals 12.116. Okay, so that red line right there. And it also may be helpful. I can label over here. So on this right here, remember our x-axis, this is months. And over here, our y-axis, this is hours of daylight. So what is that midline? In context of hours of daylight, months. It would be your average amount of daylight. Right, because it goes right through the middle of the graph, so it takes into account highs and lows. It'd be your average amount of daylight. Think Y is amount of daylight. Right? So, amount of daylight equals 12.116. That goes through the middle. It's your average. All right, what is the 1.598? That was our amplitude. What does that mean? Perfect. It is your variation from the average. So it tells us that at our highest point, we're 1.598 hours more than the average, and at our lowest point, we're 1.598 hours below. All right, what about the period of the graph? How long it takes to repeat, and what would it be measured in? Months, right? So it would be like it takes 12.27 months to start repeating. Now, knowing what we know about nature, what should that be? It should be exactly 12, right? But from year to year, there's variation. So since this was only looking at data for 1 year, that has lent itself to where we have a little bit longer period here. But the next year might be 11.92, and then the next year might be 12.04. And so if you looked at data for more than 1 year, then it would give you a more accurate period, and you would think if you looked at data for a long period of time, it should get closer and closer to 12. Exactly. All right, Y is their phase shift of 3.13 to the right. Okay, to think about this, let me graph. I'm going to graph here what this line would, click over here. I'm going to graph what this line would look like if we did not have a phase shift. So if we just had y equals 1.598 sine of 0.512, I'm not going to put the phase shift, plus 12.116. All right, so, oh, I don't have an x. That's why it's just graphing a straight line. Okay, so this is what the graph would look like if I did not have a phase shift. Okay? 1 right here, what month is that at 1? It's January. Okay, so knowing what we know about daylight, would that be right for the amount of daylight in January? It would not, right? January should be a lower point, not the minimum. That happens like December 21st, but January should be lower, right? So basically, the only reason for really any of these problems that you need a phase shift is to line it up with the data. So just to get it to line up with data. And it really wouldn't matter what the context of the problem was. It doesn't matter what you're talking about. The reason that you have to have a phase shift is to get it to line up with the data. Okay, let's look at example 2. All right, we are going to put us in some new data. I'm just going to type over top of this I already have. So we're going to move pretty quick. So if you are a quick typer, type it in. If you are slow, you might want to just kind of follow along. All right, now, these are temperatures, so we still have 1 through 12 for our X's, but our temperatures are here. I don't see my data. Why do I not see it? It's too big. Right, so you can change over here, but whoever it was that told me, there is a zoom fit right here with this little plus sign. If you just hit that, it is going to it is going to give you the best picture there. So if you just hit that little looking glass right there in the corner, mine's gone now because I hit it, but there. This one doesn't fit quite as well, right? Hours of daylight is going to be really, really close to fitting perfectly. There's going to be some variations in temperatures from year to year, so this doesn't fit quite as well, but it still follows the pattern, right? So and I just left my regression here and it adjusted. If you didn't, you can type it back in. Make sure your table says X1 and Y1 up here at the top. If your table says X2, Y2, where you like added a second table before you got rid of that first one, then that just means you're going to have to use 2's instead of 1's in that equation right there. So our model, and when it asks for a sinusoidal model, that is an equation, a sine equation. So our model is going to be 11.836 sine of 0.555 x minus 2.452. I'm just rounding to 3 places to make it quicker, right? 53.360. And so I'm moving along pretty quickly. You can see that there's a little more variation on this one with my answers. My A and my D are just a little tiny bit off. Nothing to worry about. It's just a different estimation method. It may cause you to miss it on the quiz, but I'll go back and give you points for it if that's the reason. So I'm not going to do these. Hold on. Okay, yeah. Midline of this function is going to be y equals 53.360 11.355. That's your average temperature. Your amplitude is 11.837. So when it asks for according to the model, that means your equation, not your table, but your equation. It wants to know the highest and the lowest temperatures. You can do this with your graph over here. Your highest would be 65.196. Your lowest would be 41.524. Or, if I know midline and amplitude to find the highest, I could just do 53.355 plus my amplitude, 11.837. It will give me 65.196. That's our highest. And then if I subtract 53.355 minus 11.837, that will give me the 41.524, which would be my lowest. Okay. I'm going to skip these next questions and look at example 3 real quick. This particular problem is not one that you can do with the graph. You could put in, we could do this, we could put in change these back to ones. You could put in low tide and high tide. Depth of water in the sound at high tide is 14. Depth of water in the sound at low tide is 5. Last high tide was at midnight, so you've got 0. High tide is 14. The next high tide would be at 11.83 repeating, so it's high tide again. And if I graph that, my sine function does not work. It is not going to be able to do this with just a few points. You have to have more points for it to do that. So what you're going to have to do for this is you're going to have to find amplitude, midline, and whatnot. So midline would be the average between high and low. 14 plus 5 divided by 2, so 19 divided by 2 would give you 9.5. So that is your midline. So you got y equals something sine bx plus c plus 9.5. The amplitude would be your distance from that midline to the highest point. So from 9.5 to 14, that would be 4.5. Okay. Period for this would be, if you go high tide to the next high tide, that's a full period, right? High tide, back down to low, back up to high. So this is your period. So like we were doing yesterday, you'll do 2 pi over b equals 11.83 repeating. Multiply both sides by b here. You got to do 2 pi divided by that 11.83 repeating. And that is going to give you, sorry, I know we're running out of time. 2 pi divided 11.83 repeating is going to give you 0.53097 here. So like if I type that in, y equals 4.5 sine b 0.53097x plus 9.5. Actually, let's think about this a little bit. I use sine. What would be better to use if my high tide is at midnight at 0? Let's change this to cosine. And there is one that actually matches what we're looking for. But my window's terrible because I hit that button right there. That really wasn't a good thing to do. My window is terrible, but that does fit our data points. And you can see our low point is at 5 there. So cosine was better. So some of these you're still going to have to kind of figure out by hand, but you can use a calculator to do so. All right, so I need to give you guys your worksheet. Sorry. I'm going to let you